Good afternoon, everyone. Today, I'd like to talk about our trial of developing CFD, two CFD frameworks for industrial use. One is called FrontFlow Red, and the other is Cube. My name is Makoto Tsubokura, and these are my colleagues. In our group, we are now trying to establish a digital engineering testbed on the K computer or the post-K computer. Our final goal is to establish the industry academia collaboration center in the RIKEN AICS for the purpose of development and implementation of the next generation digital engineering based on HPC. The concept of the testbed is very simple. Academia develops software for industrial use and implement it on the flagship supercomputer. And the industry members provide their needs in digital engineering, and academia optimize it for their specific use. And each company or the OEM brings their own targets to this testbed on the flagship computer, and conducting validation tests of their own, and under the support of academia. And the feature is that the academia can utilize the world-leading HPC software developed at RIKEN AICS, which is a so-called basic technology. And also, we are going to construct a sort of a consortium style for the industry academia collaboration. So it means not one by one, but we organize a sort of a consortium. And another important feature is a multiple digital testbed. And that is not a single testbed, but we develop a testbed for a specific use. So one is, for example, automotive testbed, and other ones include a combustion system testbed, a construction testbed, aircraft testbed, or something like that. And support of industrial use is done by the RIKEN AICS. So far, we have organized one consortium for the automobiles. So far, about more than 10 OEMs and suppliers are joining this consortium, and RIKEN is the center of this consortium. But not only RIKEN, but also Hokkaido University, and the University of Tokyo and Hiroshima University are now joining. It means we do not utilize not only the RIKEN softwares, but other universities can also bring their own softwares to develop some softwares for specific industrial use. And now we are now going to prepare the next consortium. That is for the combustion system, like gas turbine or something like that. For this consortium, the leader is going to be the Professor Kurose at the Kyoto University, and also we are joining this consortium, and they are going to utilize our software developed here. And the third one is going to be the construction companies consortiums. The leader will be Professor Tamura at the Tokyo Tech, and also Kobe University, and RIKEN is joining this consortium. Now I'd like to move on the software development we are now conducting. Actually, in our group, we are going to develop softwares for the fluid mechanics, and we use so-called large edge simulation. Actually, the industries are very conservative, and they use so-called Reynolds average Navier-Stokes simulations shown here. So they obtained only the averaged flow field from their simulations. But we would like to promote these types of transient and three-dimensional fluid simulations instead of these conventional simulations for the reasons of the higher accuracy, as well as expansions of its usage for beyond their expectations. And this is a so-called large edge simulation. So where you use a very fine grid, accuracy is going to be high. So it means if you use a HPC, you can obtain almost the same results as the experiments. This is a number of the numerical grids required for these simulations. There are 3 lines here, and this is a Reynolds number. Reynolds number simply means that if you go, Reynolds number is going to be high, it means the flow speed is going to be high. And here the vertical is a number of the grid required for these simulations. These three lines indicate the resolution, mesh numbers required for the direct numerical simulation shown here. This is not the largest simulation, but they solve all the turbulence. And the next one is large edge simulations, but the wall is resolved. I mean, the boundary layer is resolved. The last one is a wall model large edge simulations. But anyway, the point is that when you use K computers, how much resolution is required for each Reynolds numbers. And I'd like to show you this result. Here, this is the K computer performance. It means when you use a K computer, the maximum mesh numbers of about 10 to 11 to 10 to 12 can be treated. And when you look at the Reynolds numbers can be treated on the K computer, for the DNS, it means that you solve everything. In that case, they can treat the Reynolds numbers around 10 to 5 or 10 to 6 at the maximum. This is very interesting that, for example, when you look at a sports ball or something like that, in that case, Reynolds number is typically 10 to 5 or 10 to 6. So for the sports balls like a baseball or golf ball, you can solve everything on the K computer. On the other hand, when you look at the road vehicles, its Reynolds number is 10 to 7. In that case, it's impossible to conduct the DNS even if you use a K computer. Maybe for the next K computers, you cannot treat the road vehicles based on the direct numerical simulations. But when you use the large edge simulations, it is within the target of within the target. The last one, I do not show that result today, but that is high-rise buildings in our area. That is wind resistance simulations for the constructions of a high-rise building. In that case, Reynolds number is quite expensive. It's 10 to 9 or something like that. So of course, DNS and high-resolution LES is impossible. But this wall model LES is within the target. Anyway, our main missions at RIKEN is to develop CFD frameworks to treat these industrial targets using a large edge simulation. Also, I'd like to introduce the FrontFlow red. Actually, the history of the FrontFlow red is very old, very long. It means that the project, the national project, launched in around 2002 to develop the unstructured vertex and the finite volume method for industrial use. So history is more than 10 years, but in our team, our main mission was to optimize this FrontFlow red on the K computer. So far, the single node performance is about 10%. Actually, this is quite high, I think, for the unstructured finite volume. And for the parallel efficiency, so far they can treat more than around 10 billion numerical elements on the K computer using 10,000 numerical nodes, which is equivalent to 80,000 cores. The advantage of the FrontFlow red is we use unstructured mesh. So the surface is the accuracy is quite high because the complicated surface is reproduced by the unstructured grid. Another important feature of the FrontFlow red is that they can treat the moving boundary problems as shown here. So we can conduct coupled simulations of flows and some solid motions. First, I'd like to show you the advantage of these types of unstructured grid systems from the viewpoint of the very fundamental physics. As maybe you may know that the physics of the flow physics of drag crisis. That is the phenomena that when you increase the Reynolds number, the drag of the sphere or the cylinder is drastically decreased at some specific Reynolds number. This is called the drag crisis. So, and the physics is quite complicated, which is relating to the separations of the boundary layer on the surface, and there is a small reattachment, detecting a transition to turbulence or something like that. So if you would like to precisely reproduce these types of physics, you need a very, very fine grids on the surface. If you have a commercial software, just try to conduct these simple sphere simulations, maybe you cannot capture these tendencies. Slightly very small numerical dissipation or something like that drastically affect the transitions, and as a result of that, this tendency cannot be captured if we use software as a black box. So we first conducted this simple sphere simulations using a FrontFlow red by specially tuning the grids on the surface from the viewpoint of the reproductions of the boundary layer on the surface. So the target the parameters to determine the resolution is the boundary layer thickness, is the theoretical boundary layer thickness on the surface, and we use a prism mesh on the surface and away from the spheres with the tetrahedral mesh. But in anyways, here the delta is the thickness of a boundary layer, and we intensively change the resolutions for the horizontal directions as well as the vertical directions. This result is quite interesting. Look at that. This is a drag coefficient, okay? And we set up the same Reynolds numbers for these 4 cases. And we just change the surface resolution. At the same Reynolds number, at the same numerical conditions, and only the difference, the resolutions, the results quite different, as you see. If the grid is relatively coarse, the drag is very low evaluated. But if you increase the resolution, it's going to be higher, it's almost double. So if you change the resolutions, the drag is going to be change about twice larger. So this intensive mesh dependence test is quite important. But after this intensive test, we can finally precisely capture the tendencies of this drag reduction. Here, this is a result of this symbol is a result of simulations, and this solid line is a result. This broken line is a result of experimental data, and this red is a golf ball case, and this black one is a smooth sphere case, and it shows a very good agreement with the experiments. And I'd like to show you some flow features on the surface. This is a smooth sphere. And this is a cases of a higher drag, just below the drag crisis. And this is after the drag crisis. And the drag decreased drastically. The same tendency can be captured or can be observed in the golf ball simulation case. Due to the surface dimple, the drag crisis appears slightly lower Reynolds number. This is a well-known phenomenon, but you can capture everything on the surface when you use a K computer, and you can optimize the dimple's shape and locations, or shape locations and depths or something like that based on these simulations. And you can also observe the surface transitions in the case of golf balls. And now we have a collaborations with the manufacturers of golf balls to optimize these dimple shape. But in anyways, what I like to say here is when you use unstructured grid, and you can free tune the grids on the surface, you can obtain almost the same results as experiments for these simple geometry. So we have applied this FrontFlow red for the much more complicated cases of a road vehicle. Road vehicle is the Reynolds number is 2 orders of magnitude higher than golf balls. So we cannot solve everything, but still we can do a very precise large edge simulations. Here, our main target is we like to evaluate how CFD can reproduce the experimental data they are conducting in the industry. So for that purpose, first we are going to check that how we can precisely capture the drag coefficient obtained in the wind tunnels. And we also try to expand its uses of CFD on the HPC for the targets which a conventional wind tunnel cannot be captured. So far, industry is very conservative, so they would like to use CFD as an alternative to a wind tunnel test, but we like to expand its possibility to something which conventional wind tunnel fundamental cannot treat. Yes, this is the possibility of the HPC. As I told you, first is, of course, doing the high-resolution simulations. You can reduce the numerical error or the modeling errors in the large simulations. As a result of that, you can obtain almost the same accuracy as the wind tunnels. So near the future, with HPC, you can replace, you do not need a wind tunnel anymore. All everything can be done on the CFD. But the second thing, that is, I think, much more important. This is the real world and coupling simulations on the high-performance computing environment. By doing this, you can do some experiments. You can do some evaluations which a conventional experiments cannot be done. I'm going to show you some results of that. And last one is a big data analysis. This is actually a very new topic, but we like to conduct the simulations, running hundreds of thousands of jobs simultaneously to generate optimization map, and also utilizing that results for the using that results on the deep learnings and try to find some optimized aerodynamic shape for the road vehicle. This is the result of FrontFlow rate on the K computers to try to evaluate how the FrontFlow rate can replace the wind tunnels. This is for targets of the light vehicle that manufactured by the Suzuki. The shape is slightly different. You see, the rear angle is going to be a decrease. So the point is that our simulation can precisely capture the tendencies of the drag change. That is, first I'd like to show you the experimental data, which is shown by blue colors. That is very interesting, that when you decrease the slant angles, people sometimes say that it is going to be monotonically decrease. People guess, but that is not correct. The first decrease, then slightly increase, then decrease again. There is some interesting fluid physics behind that, but I cannot explain that today. So I will tell you later if you are interested in. But any point is that CFD, whether or not, can predict this tendency. I want to show you two results. One is the coarse large age simulation indicated by this red color. This is conducted in the conventional supercomputers used in the company. So the total mesh numbers used here is about 35 million, and the surface resolution is 2 millimeter. And then we increase resolutions on the surface down to the 0.5 millimeter, less than 1 millimeter on the surface on the K computer using the 2.3 billion numerical meshes. And the result is shown by this green color. In the case of coarse mesh, still the result is not that bad, because for this cases, drag is normalized as 1, and simulations overestimate by 7%. Just 7%. This one's case is about 10%. This one's 3%. This one's again 10%. As a result of that, this coarse mesh cannot capture the tendencies. Decrease, increase, decrease is correct, but it increase, decrease, increase. So it is NG for the industrial use. On the other hand, if you increase the resolutions from the 2 millimeter to 0.5 millimeter, as you see, all the results is within the errors of the and also it can capture the tendencies of a decrease, increase, decrease. So if you can obtain these accuracies by increasing the resolutions less than 1 millimeter, you can obtain almost the same results as a wind tunnel. So you do not need a wind tunnel anymore. And this is a result of the flow field. This is the conventional large simulations used in the OEMs, and this is a K-computer result. By increasing the resolutions, you can capture the much more smaller eddies on the surface. And this is the possibilities of the replacement of the wind tunnels by CFD. And the next result is expansions of the possibilities of the CFD to the target which a conventional wind tunnel fundamentally cannot treat. That is a coupling simulations of road vehicles and its motions, and also the driver's reaction. Here, we are compared the two vehicles subjected by the crosswind. It's a very strong crosswind of about more than 10 meters per second for the side. And it's a stepwise side wind. In such a situation, the vehicle's motion is going to be very unstable. And drivers always try to back to the original lanes when the vehicle is subjected by these crosswind. We conducted the simulations of these situations by coupling the fluid around the vehicles 6 degrees of the freedom of motions, as well as the driver's reactions. This is the result. This is the time series of a vehicle's yaw angle change, as well as the driver's reaction. That is very interesting. You do not need a real vehicle. Just you obtain the CAD data, then you can evaluate the vehicle's high-speed stability at a very early stage of development. Of course, these evaluation cannot be done these evaluation can do during the development process at a very late stage. At the very last stage, you can do that when you use prototype vehicles, but you cannot do that for the very early stage. But you can do that if you use a CFD. So this is a new possibilities of simulations. Not only the replacement of wind tunnels, but beyond the wind tunnel. So the situation is very optimistic and very happy if we show these results to industries. But always, but still, industry cannot use these simulations, FrontFlow rate, in their own production process. Why? Reason is very simple. The main problem is the mesh generation. As I told you, that when you increase the resolutions from the 2 millimeter down to 0.5 millimeter, then the accuracy is almost comparable to the wind tunnels. But when we look at the real vehicle's shape as a digital data, the digital data is something like this. This is a close-up view of the vehicle's rear end corner. There is a back door here. This is a roof panel here. This is the side panel here. The problem is that these gaps, always the CAD data or the industrial shape data increase such a gap, overlap, hole, or something like that. And when you conduct the simulations on CFD, you always have to modify the surface. In the case of the resolution is more than 1 millimeter, it's a surface repairment is quite easy. Just you use a commercial software, there you can automatically eliminate these gaps. So this is so-called wrapping technique. But as I told you, if you would like to replace the wind tunnels or experiments by CFD, resolution should be less than 1 millimeter. The gap is more than 1 millimeter. It means you cannot automatically eliminate these gaps. You have to eliminate these gaps by hand. And you have to identify this gap is really important or not. Then you have to do that manually, everything. Do you know how long does it to generate this 1 millimeter resolution mesh for the 0.5 millimeter simulation? It takes 3 months by my students. He always complained about that. But anyways, this is impossible for the industrial use. For the research use, it's okay. Academia are very happy to do these types of high-resolution simulations, asking a student to generate the mesh for taking 3 months or something like that. It's okay. But for the industrial use, it's impossible. So we would like to propose alternative. This is the second simulation called the cube. This is based on the hierarchically structured grid. And other method is almost the same as the FrontFlow rate. We use a finite volume method, but only the difference is data structure. We do not use unstructured mesh. We use a hierarchically structured mesh. The important feature of this simulation is that we do not solve not only the fluid, but also structures or something like that in the same framework. And on the surface, of course, in this case, we do not reproduce the surface precisely because we use a hierarchically structured grid. So surface is have to be modeled by using immersive boundary technique. And using this immersive boundary technique, we developed a method to repair the surface automatically. We don't have to repair the surface in this case. It is automatically repaired. And also, we develop some fluid structure coupling analysis or something like based on that. I'm going to talk about that later. But the most important thing is that two features, most important features. First, it is very suitable for the high performance computing. Hierarchically structured grid using using a cube concept. Cube concept. This is not the mesh actually. This is domain decompositions. First, we decompose the domains by using this cube. Then after that, we allocate the same number of cells for each cube. As a result of that, as long as you allocate the same number of cubes for each CPU, the computational load for each CPU is exactly the same. So you can achieve the very, very good parallel efficiency. And the second one is automatic CAD data repairment. So you do not have to generate the mesh by yourself. It's automatically generated. And, this is some typical results we obtained. This is the cases of the maximum cases. We use 27 billion numerical meshes with a surface resolution of 0.7 millimeter. As I told you, in the case of unstructured grid, you need the resolutions of less than 1 millimeter for the higher resolution, for the higher accuracies comparable to the wind tunnels. We do the same thing, so using 27 billion meshes. Guess how long does it take to generate the mesh? It takes less than 1 hour. In the case of unstructured grid, it takes 3 months. But for this, when you use this structured grid, hierarchical structured grid, it takes just less than 1 hour. And you can do the simulations. Of course, it needs much CPU time, but still, it is within the target of the industrial use. 3 months is terrible. 1 hour, less than 1 hour, it's possible to use in the industry as long as they have a very large scale hardware. And another important feature is that this moving boundary technique, but I like to skip these ones. Maybe I'm running out of my time, right? And these are the 6 degrees of freedom simulations, and this is engine simulations because we do not deform the mesh. Mesh is fixed, and we only treat the moving boundaries by using immersive boundaries. So very complicated motions can be easily captured. And also, we do not solve not only the fluid, but also the structures also be solved on the same fixed grid. This is the so-called Eulerian approach for the structure dynamics. So you can solve everything on the very single meshes of the hierarchically structured grid. And yes, this is our support of industrial use on the K computer. Here, the red one is they use FrontFlow red, and the blue one is a cube. So far, the needs is needs of the concerning the needs in the industry. The FrontFlow red and cube is almost comparable. In the case they need a very, very highly accurate results on the K computer, they would like to use FrontFlow red. But they would like to seek for the future and the possibilities of CFD. They would like to use cube. So we are now supporting these two softwares for their industrial use. And I'd like to conclude my talks by talking about 2 points. One is I would like to say that the CFD use in industry is very conservative. So still, FrontFlow red is very popular from the viewpoint of its accuracy. But if they would like to expand its possibilities using HPC, cube is very promising. This is a case you conduct the hundreds of millions of meshes simulations of a road vehicle. It takes 120 hours for the preconditioning. Simulations 120 hours and post-processing 50 hours. But if we use a cube, preconditioning is less than 1 hour, simulation is about 20 hours, and post is 5 hours. So you can drastically decrease the total time for the development. Finally, I'd like to talk about the software management. For the, as I told you, we are now developing two softwares for industrial use, and we like to develop the engineering test beds as shown here, and automotive and the combustion systems are about to launch it, and other consortium will follow. But anyways, when we develop these softwares, for the core kernel, what frameworks can be developed in our research team. But for these industrial use, these softwares have to be optimized for their own use, a specific industrial target. And after that, we need some strong support for their usage on the flagship computers. In that case, it's impossible to do everything in our team. So we need some collaborations with operation teams for these support, and also the optimizations for the specific industrial targets. Someone have to do these two things simultaneously. So these are collaborations between the research team and the operation team is going to be very important. Thank you very much.